Hello class, today we're going to be learning in lesson 3-7 in our algebra books about graphing linear functions. Now first of all we have to remember what a function is. Today we're going to be writing a function with this notation. This right here means the function of x, okay? And we can write it as just as a linear equation. It's going to look like mx plus b, where m is our slope and b is our y-intercept. Again, that means where this line, this function, is going to cross the y-axis. Okay? And what's important about a function is that we might have the value of x that we're going to plug in to this function. We call that our input because we plug it in. And in the end, it's going to produce an output. It's going to look like f of x. This is going to be our output. It's going to be the value of this function once I plug in x. And if you recall with functions, each input can only produce one output, which means if I plug in the number 2, I'm only going to get one output when I plug it in. So why don't we look a little bit more at this with some actual functions. Our first one is telling us to evaluate f of x equal to 3x minus 15 when x is equal to negative 3. So we're evaluating this function when we plug in negative 3. So I'm going to write this as having my function f when I'm plugging in the value of negative 3 every time I see an x. So I'm going to rewrite it as 3 times negative 3 minus 15. I know that 3 times negative 3 is negative 9 minus 15. And again, if I see that minus sign, I can change it to adding the opposite. So now I have negative 9 plus negative 15, and that equals negative 24. So to write my answer, I'm going to say that f of 3 in this instance equals negative 24, which means the function of 3 is negative 24. This is very similar to what you guys did before when you were solving equations. Now we're calling them functions. And I can also have a different letter in front. Okay, before I had the function f of x, now it's the function h of x. Very similar. This time it's equal to negative 7x when x is equal to 7. So I want to find out what this function h is when I plug in 7. So let's plug it in. That equals negative 7 times 7. Oh, I know this. That's going to be negative 49. And look at that. I'm already done. So I'm going to rewrite my answer by saying h. The function h of 7 is equal to negative 49. And I'm done. But we're not always looking for what the function is equal to. Sometimes we're given what the function is and have to find the input, the x. Like in this first example here, when f of x equals 2x minus 10, this time we need to find x. We need to find the input so that the output, the f of x, equals 6. All right? So this time, if I know f of x equals 6, I'm going to plug that in where it says f of x. And I'm going to set that equal to the rest of this function, 2x minus 10. And now, like I've done many times in the past, I'm just going to solve for x. So first I'm going to get rid of my lonely number by adding 10 to both sides. I know that negative 10 and positive 10 is going to cancel out. So on the left-hand side, I have 16 equal to 2x on the right-hand side. One more step to get the x by itself, divide both sides by 2. And I'm left with 8 equals x. And I really like to rewrite this so that the x is on the left-hand side. So I'm going to put x equals 8 when f of x is equal to 6. So this is my final answer. I needed to include this last part when f of x was equal to 6, which is what I was given in the beginning, so that I know when x is going to equal the number 8. So why don't we do this with one more function. I'm going to call it g of x this time. So the function g of x, but it is going to be finding x so that g of x equals 16. So again, where it says g of x, I'm going to plug in my value of 16. I'm already given the output, but I need to find the input to make that true. So I'm going to set it equal to the rest of the function, negative 2x plus 4. And my goal is to get the x by itself. So first I need to get rid of the lonely number. Instead of adding 4, I'm going to subtract 4 on both sides. 16 minus 4 is 12, and that's equal to negative 2x, because the 4 minus the 4 cancel each other out. Now to get the x by itself, divide both sides by negative 2. 12 divided by negative 2 is negative 6. And that is just equal to x. And again, I'm going to rewrite this as x is equal to negative 6. And I'm going to throw in the when g of x is equal to 16. And that is going to be my final answer. So what we've done on these past 4 problems has been doing some calculations with these functions, but still we haven't graphed them. So what's really important when we're graphing is to think of the most basic line of a function that we've seen, okay? And this line goes straight through the origin, and every single coordinate is the same number. So this is 1, 1, this point is 2, 2, this point is 3, 3. Even down below, this one would be negative 3, negative 3, and so on and so forth. And what this function is called the parent linear function. And what it looks like is the function f of x simply equal to x. So as you can see, all of these points, if my x coordinate is the number 1, the y coordinate is going to be the same thing, and we're going to say that it's f of x. So if I plug in 1 into my function, the f of x is also going to be 1. If I plug in negative 3, the function at negative 3 is still going to be negative 3. So this is the parent linear function. And what is very important is for us to be able to relate this line of this linear function to any other linear function we graph. So let's do that. I've already drawn the parent linear function for you. We know is f of x equal to x. And this time I have a new function, g of x, and it's equal to x plus 3. Now without even graphing this function, why don't we just try to describe some of the similarities and differences between our two functions. Looking right away, I can see that they both have the same slope. They're both written in the slope-intercept form, so I can see that their slope for both of them is going to be positive 1. And if they have the same slope, I've learned in the past that this means that they are both going to be parallel to each other. The only difference is going to be where they cross the y axis. So in this case, the g of x y-intercept is at positive 3. It doesn't look like there is a y-intercept here. Okay, so that means that it's going to be 0. That's going to be my y-intercept. It's going to cross through the origin at 0. So since I already have my parent linear function graphed, why don't I graph the g of x now? I'm going to start by plotting where it's going to cross the y-intercept, the y-axis. That's going to be at positive 3. And from there, I'm going to use my slope to chart one more coordinate. The slope is positive 1, so that means I'm going to go up 1 and to the right 1. And I can plot my point right there. I'm going to take my ruler. I'm going to connect these two dots. And let's see here. Perfect. As you can see right away, both of those lines are parallel to one another, all right? But the second line, the g of x, the function, crosses at positive 3 instead of crossing down below at the origin. Again, I'm given a different function. This time h of x is equal to 2x. And I want to first compare it to the parent linear function, the very basic one of just simply f of x equal to x. And just like we did before, let's compare. Let's start at looking at the slope of both of them. Now the slope for f of x is that invisible 1, but the slope for the h of x is positive 2. It's a bigger slope, which means that when you're going up the mountain, I should be expecting to see it looking a lot steeper, okay? Now when I'm looking for the y-intercept, neither one have a value for the y-intercept, which means that it's going to be 0. So that means that they're both going to cross the y-axis through the origin. They have the same y-intercept. So I already have the f of x, the parent linear function, graphed for you. So why don't we graph our h of x? Okay, we're going to start at the y-intercept where it meets at 0. So that's at the origin. And from there, I'm going to look at my slope. The slope of 2 is the same as 2 over 1, which means I'm going to rise up 2, and I'm going to go to the right 1. I'm going to take my ruler now, connect just those 2 points. And just like I had predicted, the slope is definitely much steeper, but they do both pass through the origin. So if you were climbing up this red mountain, it would be a much more difficult task because the slope is greater, okay, than the parent linear function. So let's look at one more. Again, I already have the parent linear function graphed for you, the f of x equal to x, passing through the origin. Just like I've done in the past, I'm going to compare the slope and the y-intercept to my new function. This time, the g of x is equal to negative 1/2 times x. So let's compare their slopes. The slope of the parent linear function is that invisible 1, but this time, not only do I have a smaller slope than the parent linear function, but it's also negative, which means the direction of the line is going to go in the opposite direction. It's going to go downhill, if you recall from before. Neither one of them have a y-intercept, so again, their y-intercept is the same. It's going to be 0. They're both going to pass through the origin. So I've compared it out loud, so let's see if that's all true. So the slope for f of x was positive 1. If the slope for the function g of x is negative 1/2, it's going to be a smaller slope, but it's also going to go the opposite direction. So starting at the y-intercept, where it crosses at 0, I'm going to put my first point. And now if my slope is negative 1/2, that means I'm going to go down 1, and I'm going to go across 2. So my rise is down negative 1, my run is positive 2. When I connect these two lines, as you can see, going downhill is a far easier slope to walk down. Okay, it's not as drastic as positive 1, but it is also in the opposite direction, and it passes through the origin. So I hope that this has helped you guys to be able to compare the slopes and the y-intercepts and what a line just might look like before you even graph it, especially when you're comparing it to the parent linear function. So come with any questions you might have to class, and I will see you there.